Hello everyone. Today we are going to talk about atomic structure. This crash course of atomic structure is very important because this crash course deals with the basic principles to advanced topics. Atomic structure forms a foundational concept for understanding chemistry at the molecular level. For JEE Main, you easily score 4 to 8 marks, sometimes 12 marks also from this chapter. It is crucial to grasp various models and principles that define atomic behavior, electronic configuration, and quantum mechanics. So without any further delay, let's get started. Our first concept over here is that Dalton's atomic theory. I'm not going deeper into it. I'm just going to tell you the main postulates, which is matter is made up of very small and indivisible particles, and atoms neither be created nor be destroyed. And these are the simple things. And also we learnt about atom is the smallest particle of the element which take part in the chemical reaction. So atoms of same element, for example, nitrogen gas, are identical in all aspects like shape, size and mass. Sometimes the question can be asked from here. And atoms of different elements like H2O have different masses like hydrogen, oxygen, different masses, shape and size. Similarly, atoms of different elements combine to form a fixed ratio. This is what we talked about law of definite proportion or constant proportion in chapter 1. It combines in the fixed ratio of small whole numbers to form a compound. Atoms are called molecules. Okay, for example, NH3, ammonia and everything. So this is what Dalton talks about his theory, and after that masses of electron, proton, neutron are comes into the picture. I don't want to tell those theory stuffs over here. Then now we are going to move on to the second atomic model, that is Thomson model. Thomson model is also known as plum pudding model, as you know why. Because if you are considering the pudding as a positive part, like an atom, the plums are electrons. That is what the Thomson thought about the atoms. But Rutherford gold foil experiment said that clearly what is atom. So he explains it to the gold foil experiment, where the alpha particle strikes the gold foil with varying deflections and reflections. For example, here you can see some rays go straight. Some rays are getting deflected by the angle less than 90 degree. Some rays are getting deflected by the angle 180 degree, and some rays are going about more than 90 degree. Right? So what does it mean? It explains how the atoms are arranged, how the microparticles inside the atoms are arranged. These observations we found out using Rutherford gold foil experiment. First of all, what are the particles, alpha particles, go straight are much more than the others, which explains most of the atom space is empty. Most of the space in the atom is empty, and the second fact is that few alpha particles are getting deflected at large angles, as you can see here, which indicates the presence of a heavily positive charged body. Large deflection, so the presence of heavily charged body which occupies the small part inside the atom. Okay, and the particles which are getting deflected at 180 degree backwards, which indicates that this heavily positively charged body is occupying very small amount, and rest of the things are empty, and inside that there were some electrons are occupied, so that these alpha particles are getting deflected. Now next we move on to some terminologies. Since this is the crash course, I don't want get deeper into each and every concept. I'm just doing the brush up. I'm just doing the revision of those concepts. Okay, because so that we'll get a time to solve some questions. Okay, let's talk about the important terminologies. I'm omitting atomic weight and molecular weight and what are so. Let's get into it. First of all, isotope. Isotope, as you know, atoms which are having the same atomic number but different mass number. For example, hydrogen 1 1, hydrogen 1 2, hydrogen 1 3. What are these? These are isotopes: hydrogen, deuterium and tritium. Right? They are having different mass numbers. The second one, which is isobars. Isobars are atoms. They are having same mass number but different atomic numbers. For example, let's say phosphorus 32 and sulfur 32. Phosphorus, the atomic number is 15, and for sulfur the atomic number is 16. These are isobars. You can expect a question from these terminologies: isotopes, isobars, and we are going to see a few more. The third one, which I want to say, that is isotones. These are the atoms having same number of neutrons but different number of protons or mass number. For example, let's take carbon 14, oxygen 18, oxygen 16 and nitrogen 15. So the atomic numbers are 6, 8 and 7. What about the number of neutrons? 14 minus 6, that would be 8. 16 minus 8, that is 8. 15 minus 7, that is 8. So same number of neutrons, these are isotones. In your question paper, just do the math and answer to these questions. As simple as that. The fourth one, which is very important one, that is isoelectronic. The atoms or molecules are cations, anions, whatever the ions may be, it can be of neutron molecule, which are having same number of electrons or isoelectronic species. Say for example, N2, which is having 14 electrons. CO, 6 for carbon, 8 for oxygen, so 14 electrons. Once again, talking about ions, Cn minus, 6 for carbon, 7 for nitrogen, so total 13, and I'm having a minus charge over here. How can I forget that? So total 14 electrons. So these are isoelectronic species, isoelectronic to each other. In previous year papers, you can come across lots of this kind of question. What is isoelectronic species, or find the isoelectronic species in the given list. You can expect this kind of questions. And finally, most of us won't talk, but I think this is also important, talking about isostars. Isostars are the molecules having same number of atoms and also same number of electrons. For example, if you can take N2 and CO. CO I'm mentioning, carbon monoxide. What it says, same number of electrons and same number of atoms. Both are diatomic molecule, and electron count 14, 6 for carbon, 8 for oxygen, in total 14 again. So this is isostar. Okay, so these are the important terminologies you should be noted down. Now let's move on to the next important part, that is wave characteristics. Why we need to study the wave characteristic? Because the upcoming questions who are dealing with the hydrogen atom, who is dealing with the particle moment and so on, so which can be asked on the basis of this. What is wavelength? Find out the wavelength, find out the wave number and do the conversions. This kind of question can be asked from this part. So it is very important to know the relationship between these terminologies. First of all, what is wave? Wave is consist of the crest and troughs. The upper part, the maximum point, that is called crest, and the minimum point of the wave, that is called trough. Is it clear? Now let's move on to the important terminologies. That is the first one, wavelength. Wavelength, as the name indicates, it is the distance between the two waves. You can take the distance between the two crests, or you can take the distance between the two trough. That is wavelength. Wavelength is indicated by or denoted by the symbol lambda. Wavelength usually given in the units of nanometer or centimeter. Sometimes they will give you in Armstrong. In that case, you need to do the conversion. That is 1 Armstrong is equal to 10 to the power minus 10 meters. Note it down. 1 Armstrong, which is equal to 10 to the power minus 10 meters. Now let's move on to frequency. Frequency is the wave. Let's take a particular point in a wave. Okay, how many waves are passing through into the given point is called frequency per second. To be more precise, in 1 second, how many waves are passing through that particular point? Okay, so that is frequency. You can imagine, you can compare it with how many buses passing through your bus stop per hour. Okay, that is also frequency. So at a given point, how many waves are crossing, that is frequency. It is denoted by the symbol nu. And this is expressed in the units of hertz or cycle per seconds. 1 hertz, which is equal to 1 cycle per second. The relationship between frequency and wavelength is much important. Why is it so? Because it is inversely proportional. Once you find out the wavelength, you can easily find out the frequency and vice versa. Okay, so what is the relation? Frequency is inversely proportional to wavelength. Why is it so? Because if I'm having small waves which are having very small wavelength, then that would be considered as a small waves, right? At a given point, the small waves can move across per given second. But if the wave is larger, then the count becomes smaller, right? So the wavelength increases, the frequency decreases. Now let's move on to the third, that is velocity. We already know about velocity in those physics stuffs. Velocity, that is the distance traveled by the wave, otherwise the speed. The distance traveled by the wave in 1 second, it's called velocity. It is denoted by c when it's expressed by per second, right? So centimeter per second. So you can write, instead of this proportionality constant, you can write nu is equal to proportionality symbol. You can write nu is equal to c by lambda. Kindly note it down, these formulas, I also attach the formula sheet, the one sheet of all those atomic structure formula in the description. But anyway, you note it down. Write those formulas and do the calculation whenever you are practicing so that it will stick your mind for the longer period of time. Okay, let's move on to the next concept, that is wave number. It is defined as the number of wavelengths per centimeter. In a given unit of space, how many waves you can ride. Once again, you can see if I'm having a box. Okay. If I'm writing the waves like this, which are having the wavelength small, right? The wavelength is small. Let's consider the same size of box. If I'm writing the big waves, it just occupies only 2, right? What I'm trying to say is wave number is also inversely proportional to wavelength. Wave number is referred as nu bar. Okay, nu bar, which is equal to 1 by lambda. Or you can write it like nu bar, which is equal to nu by c. Because we know that nu is equal to c by lambda, just do the substitution and you got the formula. Okay, so another thing is amplitude. Amplitude is the height of the crust. As you can see here, the overall height of the crust or trough is amplitude. It is denoted by the symbol A. Why that is so important? Because it determines the intensity or brightness of the beam of light. So if that is having more amplitude, the light will be more brighter. Now let's move on to the crucial part of this chapter, that is electromagnetic radiation, EMR. So I just want to give you the brief about what are the rays are over here and how to memorize it and what is the relationship. That is more important over here. Okay, so what are the waves are present? Starting from here, radio wave, micro, infrared, visible, UV, X-ray, gamma ray. Why the order is also important? Because as the wavelength decreases, the frequency and energy increase. This relation is very important. Why I'm mentioning how this is related to the order? Because you can see this is arranged in the increasing energy, right? So energy increases means wavelength decreases. Particularly this point, the visible, which comes under 350 to 700 nanometer. The question can be asked in this part, what frequency it comes under, and so on. So how to remember this order? You can go about the simple mnemonic Rohan, Mishra, visited Uncle Xavier's garden. How that is related to EMR? Rohan, M for microwave, I for IR, visited, visible, uncle, UV, Xavier's, X-ray, garden, for gamma ray. Clear? Noted? Now let's move on to the next important part, that is atomic spectrum. What is atomic spectrum first of all? Let's say you are giving some energy to an atom. Always the electron speaks. That is a representative of the atom, isn't it? So it gains that energy, it observes that energy and goes to the excited level. It gets excited. If we are having more energy, we'll dance, sing, and trying to lose that energy, right? So similarly, the electrons is also behaving as you know, it absorbs the energy and goes to the excited level. From ground state to excited state. Upon moving from ground state to excited state, what kind of wavelength this electron absorbs the energy, that is recorded, that is called absorption spectrum. Similarly, once it coming back from excited state to ground state or lower energy state, it releases that energy, right? Then only it can come back. So that spectrum is recorded, that wavelength is recorded, that is called emission spectrum. That is as simple as that, emission and absorption spectrum. Why that is so important? Because we checked it with hydrogen atom. Hydrogen atom, as we all know, which is the simplest atom, which is having only one electron, so we don't need to care about which electron is going there. So we had just tested with hydrogen atom. We found some series, some lines over there. So the entire spectrum consists of 6 series of lines. They are Lyman, Balmer, Paschen, Brackett, Hund. What is this map? Okay, let me explain it in this way. Let's say I'm starting a point of n is n1, that is the lower energy state. Similarly, I'm having some states for excitement where the electrons can go and reach. Okay, so these are, say this is energy level 1, 2, 3, 4, 5, 6, 7. If an electron goes from first state to N2 state, or first state to third state, fourth state, and so on, those lines are called Lyman series. First state to the consequent states, those are Lyman series, and that series can be observed in UV region. Okay, and whatever I am writing in this part and in this crash course, these are very, very important. Don't omit anything. Then Balmer. Similarly, I'm starting it from the electron start from second state to third state to fourth state to fifth state and so on. Those are Balmer, and observed region is visible. These regions are also important while solving the problems. These N1 and N2 are also important. Paschen. It's starting from 3, goes on to 4, 5 and 6, 7, 8 and so on. Bracket starts from fourth state, fourth energy level, goes to 5, 6, 7, which can be observed in IR region. Hund, fifth state to 6, 7, 8, 9, 10. And those are also observed in IR region. As I told you, these questions are also important, right? These regions, these numbers are also important. Let's try to solve this question, which is asking for the shortest wavelength in Balmer series of hydrogen spectrum is what? These are previous year questions. Calculate the shortest wavelength in the Balmer series. Balmer series means it starts from second state to 3, 4, 5. So how we can solve it? N1 is equal to 2, right? And N2 is 3, 4, 5 and goes on. They are asking for shortest wavelength. We don't know which region it just attained, so I'm taking it infinity. And what is the formula to solve this? They are asking for wavelength, is it? So you can note down this formula, which is super important. 1 by lambda, that is what? Wave number, equal to r into 1 by n1 square minus 1 by n2 square. What is r? That is the Rydberg constant. The value is so big, but it's okay. 10.9768 centimeter inverse. Just we are going to apply that over here. 1 by lambda equal to r value they have given in meter inverse, so we can take it as such. 10 to the power 7 n1, that is 2 square, minus n2, that is 1 by infinity, that will come 0. So 1 by 4. So 1 by 4 into 1.097 into 10 to the power 7. You just have to take that inverse, right? So that I can get a wavelength. So which comes out to be 364.7 nanometers. Okay, that will come around 4.09 something. So just take an inverse of it, that will come 364.7 nanometer. Okay, this is the one kind of question can be asked. The another kind of question can be asked from this part, because as I told you, this is super important part. That is, although this is an JA advanced question, but I always suggest my students to do one level extra. Okay, so here you can see the number of spectral lines emitted when an electron in hydrogen atom cascades from n is equal to 5 state to n is equal to 2. It is an emission spectrum, right? So n is equal to 5 state to n is equal to 2. So how we can solve this? For that we need to understand the emission spectrum, right? So what is emission spectrum? When that is coming back to the original position or lower energy level, it emits some amount of energy that will be that frequency is captured and talks about the emission spectrum, right? So here you can see it comes from n is equal to 5 to n is equal to 2. 4, 3, 2, 1. So 5 to 2. How many spectral lines can be emitted? Here you have to note down one thing. The electron can come in several ways. It can jump, or it can come through straight, or it can go step by step. For example, here you can say that from fifth state to fourth state it can come. From fifth state it can go to third state. From fifth state it can go to second state. Only second state. So then from fourth state it can go to 3. From fourth it can go to 2. Similarly from 3 it can go to 2. So how many in total? 1, 2, 3, 4, 5, 6. So there are total lines are 6. 6 is the answer. This question is very simple questions for very advanced level, but still asked in that paper. Lucky guys. So note it down. This kind of question can be asked. So now let's move on to atoms and electrons. Bohr atomic model. So what he suggested about the atoms and so on, so those are not much important. What is important there over is they are revolving like a circular path, right? If there is a circular path, there must be angular momentum. That is provided by MVR, right? So we know that these how the emission happens and how the electrons are getting emitted in the form of photons and quantums, right? Sorry, I'm telling it again. The substances, if that is releasing in the small packets or bundle of energy, that is called quantum, and if in case that bundle or quantum is in case of light, then that would be photon. Okay, that is the difference between quantum and photon. Okay, so the energy of the quantum is directly proportional to the frequency, right? How much over the frequency increases, the energy is also getting increased. We saw that in AMR also. So how we can write it? We know that is E is equal to h nu, the particle nature, h is a Planck constant, so on. So why that is important over here? Because Bohr atomic model says for a finite number of circular orbits where the electrons are revolving, the electron the angular momentum of an electron is an integral multiple of the factor h by 2 pi. Integral multiple, which means that 1, 2, 3, 4, something like that. So the whole number multiples. So for that I'm mentioning n. So MVR is equal to NH by 2 pi. This formula is also important. And then energy observed or emitted when that is going back, when that is doing the jumping, going to the excited level and coming back to the lower level. When they are doing the jumping, how we can calculate the energies? That energy can be calculated in the way delta E is equal to E2 minus E1. Energy, that is h nu, that we know. E2 minus E1, that is more important. What is E1 and E2? Electrons in the second and first energy levels, those are called E2 and E1. E1 and E2. The Planck constant value they have given. And one more thing I did want to add over here, that is sometimes the question can be asked in this part, find the radius of the nth orbit of atom. Find the radius. Okay, for that you can simply apply here Z denotes the atomic number, n is the level of which orbit that they will give, and sometimes they will give the radius and ask you to find the n value. Those calculations you guys can draw. And formula is Rn is equal to 0.509 into n square by z in Armstrong. The values, the formula I have given in Armstrong. Please note that. Okay, so let's solve problems related to this. The ratio of energy of an electron the ratio of an energy of an electron from fifth orbit to that in second orbit of hydrogen atom is. They're just asking us to find the ratios. So energy, which is equal to, I'm giving you the new formula over here for this kind of question, minus 13.6 n by n square, which is in the unit of electron volt. Okay, so what is the energy change over here from fifth orbit to second orbit, right? So you can substitute it. N2, so which comes out to be can just substitute it. We are just asking about the ratios E5 to E2. Square 25 and 2 square, that is 4. So it will comes out to be 4 by 25. So 2 by, sorry, so 4 by 25 in more simplest form. You can write it in decimals. It's depend on the answer they have given. 0.16. Okay, so this kind of question you can expect in this year J main paper. Then the question which was asked, calculate the frequency of radiation emitted when electron jumps from n is equal to 5 state to n is equal to 2 state of helium atom. So helium atom means atomic number 2, right? So RH value they have given, C value they have given. So what we have to do is, we know that delta E, which is equal to Hc by lambda, right? So what is lambda? Hc by lambda, that is R into 1 by n1 square minus 1 by n2 square. So that is equal to n1, that is 2, and n2, that's to be 5. Let's substitute the values. You will get an answer. To the calculation, you must be getting an answer of wavelength. Here we have the simple question which is asked in JEE Main 2019. Kindly note it down, this question, solve it and let me know the answers. Okay. So you can use, I can give you the hint for solving this problem. You can use the formula we have discussed just before, both the frequency and wavelength relationship. Okay. So now it's time to move on to the next part, that is quantum numbers. Quantum numbers are of four types. Four different quantum numbers are there: principal, azimuthal, magnetic and spin. So the symbols and the values which is clearly given, what I would say is try to write the quantum numbers for at least 10 to 15 elements. Pick up some elements randomly and then try to write the quantum numbers of those. Okay, principal quantum number is nothing but the shell. Okay, KLM, that shells. And azimuthal quantum number, those are the subshells, SPGF. Okay, magnetic quantum number, which is related to the azimuthal. Why I am saying like that? Because it starts from minus L to plus L. Let's say azimuthal is 2. It is starting from 0 to n minus 1, is it? So let's say this azimuthal is 2. L value is 2. So it is 0. It will comes out to be from 0 to minus 2, minus 1, 0, plus 1, plus 2. Okay, so that is magnetic quantum numbers. Azimuthal for 2, which is 0 for S, 1 for P, 2 for D, 3 for F. Mostly they'll ask up to F. So these are the numbers for azimuthal. Okay, talking about spin, there is only 2 spins of opposite direction, clockwise and anti-clockwise. So plus 1 by 2 and minus 1 by 2. Right? So the formulas. These formulas are super important. So kindly note it down. Particularly the first one, that's very, very important. Okay, so now let's solve some questions based on this. The simple question asked in JEE Advanced 2019, which is for an electron in 3D orbital, 3D, okay, determine all possible values of principal, azimuthal, magnetic quantum number and spin. So as I told you, principal quantum number is nothing but the shell. So n is equal to 3. Third shell, right? Azimuthal quantum number, that is subshell. D, so L value is, I told you, that is 2. And magnetic quantum number, minus 2 to plus 2. Spin quantum number, plus 1 by 2 and minus 1 by 2. Right? So this kind of question you can solve it. You can try solving it for different levels. I can suggest you to do other d orbitals and some 4f. You can try it out, and otherwise they will give you the atom name and ask you to find the principal quantum numbers, okay, of the second shell, something like that, principal and following quantum numbers for by giving you the atom name. 4f you can try it out with 5s, and you can try it out with 6p. Okay, these questions can be asked. Then calculate the maximum number of electrons that can be accommodated in all orbitals with n plus L is equal to 4. What is n plus L is equal to 4? N is principal quantum number, L, that is azimuthal quantum number, right? So in total I have to get 4. Let's say n is equal to 1 and L is equal to 3. Is it possible? For this first shell, the L can't be 3, right? The first shell, there is only one subshell, that needs to be S, that is L is equal to 0. So this combination is not possible. Then n is equal to 2, L is equal to 2. Is it possible? No. Second subshell D subshell is not possible. Then let's move on to n is equal to 3 and L is equal to 1. Is it possible? Yes, it is. Similarly, you can try it out with other possibilities. N is equal to 4, L is equal to 0. Is it possible? Yes, it is. So what are the maximum number of electrons that can be accommodated? So for example, if I am taking N is equal to 4, L is equal to 0, then that is 4s, isn't it? So number of electrons 2. And if I am considering 3 P, six electrons. What about 3D? Then that is not possible. So total of 8 electrons. Now let's move on to the next part, that is shape of orbitals. This also plays an important role because of these radial nodes, angular nodes part. What is nodes first of all? Where the maximum, the probability of finding an electron is least. Okay, so that is called node. Okay, where I can't find the electron in the atom, because I have told you atom is mostly consist of empty spaces, right? So where I can't find the electrons, do they have that kind of places inside the atom? Yes, we have. So talking about radial nodes and angular nodes, this S orbital, that is spherical in shape, the number of radial nodes that you can count it from n is equal to n minus 1 formula. Let's say n is third shell. So third shell, 3 minus 1, so the radial node is 2. Okay. Similarly for the P, that takes dumbbell shape, as you can see here. And you have to observe one thing, in dumbbell shape, these are going as across the axis. It's going across the axis. It's not in between, it's going across the axis. Okay, that is also plays a very important role. So what are the orbitals are going in between? That question was asked in, if I'm not wrong, that is asked in 2016. So dumbbell shape, radial node n is n minus 2. So for example 3p, 1 radial node. And for the angular node which indicates the where I can't find the electrons, right? So you can see the in-between part. Although I'm mentioning that as in dumbbell shape, dumbbell I'm referring to as a two lobes are almost touching each other. So in between this part is the one where I can't find the electrons. Okay, that is our node. Okay, so for P there is only one node, and for D that is having double or clover leaf, which is having 2 positions, and these are between the axis. As you can see, the XY, between X and Y axis I am like the clover leaf is occupied. So similarly, Y and Z axis, It is going between the axis x and z axis. So it goes like that. And n minus 3, that is for radial node. The angular node is 2. And for F, angular node is 3. Radial node's formula, that will be n minus 4. If they are asking for total number of nodes, okay, total nodes, radial plus angular, you can remember a simple formula, n minus L minus 1. So the L comes for the angular node. Okay, so if you are omitting L part, then you will get radial node. Angular node, you can write simply the L value. Okay, and talking about these shapes, these z square, these are going across, more precisely along the axis. Along the axis. Sorry, along the axis, and here in d square I'm having the electron cloud in z axis. Okay, hope the orbital structures are clear to you. Now let's move on to the part where how to fill up the electrons. These are simple ones. 3 rules are there. I'm telling you in simple words. The first rule, Pauli's exclusion principle, which says that only 2 electrons can occupy in the same orbiter. For let's say if I'm taking S, so these 2 electrons can occupy. In case of p orbital, I can occupy 6 electrons normal, but still we have the directions, right? So px, py and pz. So 2 electrons only. If you are taking D also, if you are taking F also. So you can, it can accommodate only 2 electrons in a orbital, but those 2 should be opposite spin. That is also important. You can't write it like this. That's a bad way of writing. That is, you should not write it like that. That is the first rule. The second rule is Aufbau principle. The electrons should fill in the order of increasing energy. First energy level, first shell, second shell, third shell, and goes on. Here you can find the twist. After 3p, 4s will come and then goes to 3d. Because of that, the energy levels of 3d and 4s are close to each other, and so and so reasons. When we discussed about the chapter, we saw that in detail. Here you can see this is important. Where you can apply this is the exceptional case of chromium and copper. Why chromium and copper are having this exceptional property? Because due to the stability of half filled and fully filled. This is fully filled 4s2 orbital structure is there. That's why it makes it much more stable. Rather than taking up 3d10 or 3d5 4s1, it is taking up 3d4 4s2 and 3d9 4s2 for chromium and copper respectively. And the third rule, which is talking about how the electrons of same energy, the degenerate. You can see let's say I'm taking p orbital. For oxygen, 1s2, 2s2, 2p4, is it? So I have to fill the electrons 1 each first. After that I can do the para. For example, I should write it like this. I should not write it like this. This is also 4 count, this is also 4 count. But you should follow the Hund's rule. You should orbital of the same energy, you should fill up the electrons of 1 each and then pair it up. That is the third rule says. Okay, these are the basic rules. We already saw about these things in while we discuss about the chapter. I'm just doing the pressure. Okay, the next part, that is wave nature of light, the dual nature of light. So first of all, the wave property. In case of photon, the wave energy which is equal to h nu, is it? And in case of particle nature, that becomes mc square, is equal to mc square from Einstein we are taking. By combining these two, for energy, h nu is equal to mc square. But we know that nu is equal to c by lambda. We already talked about it. Velocity by wavelength. So I'm just going to substitute that over here. So h nu, instead of that, I'm just giving mc square. So 1c will get cancelled out, and then remaining h by lambda, which is equal to mc, right? So c, it is a velocity of light, and in case of waves we'll talk about that velocity. So I can take that as nu, I can take that as v, right? So if I want wavelength, which is equal to h by mv. So what is mv? Mass into velocity, this momentum, h by p. So this formula, please note it down, this is super important. Then Heisenberg uncertainty principle, which talks about you can't find the position and the momentum of a particle, of a microparticle at the same time simultaneously. So this formula plays an important role, which talks about delta x. X is for position and p, which is for momentum. P can be replaced with mv. Mass is not changing, only the velocity is getting changed. So delta v. You can try out the problems using this as well. I'm attaching one problem sheet where you can find more problems for practicing purpose. Then we are going to talk about the de Broglie equation, which talks about for a stable orbit. I told you electrons are moving in the circular orbit, right? So the circumference will be the whole number of the wavelength. So 2 pi r, which is equal to n lambda, integral multiple of the whole number of the wavelength. Using the de Broglie equation, you found out this formula. This is more important. mvr is equal to nh2 pi. We already saw this, how we can derive that. Okay. Then we'll solve these questions. Calculate the de Broglie wavelength, that is lambda, for an electron accelerated through the potential difference 100 volts. Given Planck constant value, they have given mass and E value, charge, that is also given. Potential difference is 100 volt. So we know that the formula for de Broglie wavelength, h by mv or h by p, but they are not referring to this. In this case, if they are asking for de Broglie wavelength given that the potential difference, simply you can substitute the values in this formula to mev, which is h is 6.236, root of 2 into mass 10 to the power minus 31, E, that is 1.6 into 10 to the power minus 19 coulombs, and V, that is 100 volts. So upon solving this, you will be ended up with a 1.23 into 10 to the power minus 10 meters. Let's solve this problem, which is asking about a photon and an electron have the same de Broglie wavelength of 1 into 10 to the power minus 10 meters. Calculate the ratio of their velocities. New photon versus new electron. We know that the formula, which is lambda is equal to h by mv, which is in case of electrons, that is h by mv, and then in case of photons, then that will become h by mc. So let's take h by mc, which is equal to h by mv, because wavelengths are equal. In that case, the values will get cancelled out. We'll get c by v, that is c by, from here I'm getting that v is equal to h by m lambda, right? I'm going to substitute the rest of the values over here. C value 3 into 10 to the power 8, H value 6.626 into 10 to the power minus 34 joule second, and mass, which is 9.1 into 10 to the power minus 31, and lambda, that is given 1 into 10 to the power minus 10. So upon solving this, I'll be ended up with approximately 400. Just match it with the given options. You'll get 437 as your answer. Okay, that kind of question can be asked mostly in MCQs rather than asking in numericals. Numericals, they will give you the values easily that can cut off or easily calculatable. Okay, so don't worry much about the calculation part. Okay, so there are some Schrodinger's wave equation is given. What that is important over here is that this model talks about the 3D waves moving around the nucleus, orbitals, right? So in that case, he uses something like wave function psi, which helps us to calculate where the electrons are most likely to found. Probability of finding the electrons. Okay, the psi represents the amplitude of the electron wave. It can be positive or negative. By itself, psi does not have any physical meaning. So it's just a amplitude for a crest and trough, the lane, right? And the probability psi square, which represents the probability of finding an electron in a particular region. Okay, it is always positive. Please note that psi can be positive or negative, but psi square, it is always positive. Higher the psi square value means higher chances, because the probability getting increased, right? So chance of finding an electron there. Okay, so these three are the important points about the Schrodinger wave equation. And the last part of this chapter, which is photoelectric effect. I'm just going to give you the brief about photoelectric effect. What is that? We are applying some energy to the metal and the electrons are getting ejected. When the electrons will get ejected, when the light hits the metal above its threshold. What is threshold? Threshold is a minimum energy that requires. Minimum, if I want to move, if I want to dance, if I want to sing, certain amount of energy must be needed, right? So once I get some energy, I can move, I can dance, I can sing. So that is called threshold. So if certain frequency, minimum frequency required to eject the electron is threshold frequency. Minimum frequency minimum energy required to eject the electron is threshold energy. Okay, only that minimum frequency of light can eject the electron. So how we can relate that frequency and energy relationship, which is E is equal to h nu. If I passed more than the threshold energy, then what will happen? These electrons will get the remaining energies, that is called our kinetic energy, the energy possessed by the ejected electrons. Okay, so that we can calculate it by h nu minus h nu naught. Nu naught represents the threshold frequency, nu is a frequency. These values will be given in the question. They can ask either find the threshold frequency or find the kinetic energy. So these two formulas are also important. So here I am attaching the formula sheet as well as the question for practicing. Please take down, and I have included solutions also. So get that, do practice more, because practice makes a man perfect. Thank you.